Hi guys, and welcome back to the ACE Academy. In this video, we will be looking at the natural parabolic function or the natural quadratic function. Now, we are going to approach this function in the same way that we approach the linear function, which would be we will first learn the natural function, then we will apply our vertical shift and our change in shape, and that will help us understand this function much better. Okay? Now, like I said, our first step is to sketch the natural linear function because that is the focus of this video. Now, the natural quadratic function has the equation of y is equal to x squared. Now, this differs in only one aspect from the equation for the natural linear function, and that would be, in this case, our x is squared, meaning we are saying x times x is equal to y. Now, using the same principles that we used to obtain the natural linear function, we are now going to plot this natural parabolic or natural quadratic function. Another thing that I want you guys to take note of is the fact that this function is called the quadratic function because it is made up of a quadratic equation. That is an equation in which the x variable is raised to the power 2, right? So instead of it being x or x cubed or x to the power 4, it is raised to the power 2. It's x to the power 2. That is what we're focusing on, right? Now, applying the same principles, if we're looking at 0, 0 times 0 is 0. So we will plot 0 times 0 at 0. 1 times 1 is 1. So we will plot it at x value 1, y value 1. 2 times 2 is 4. So at x value 2, we are going to plot it against y value 4. Right. 3 times 3 is 9. So at x value 3, we are going to plot it against a y value of 9. And of course, we cannot do 4 because we don't have the points 16 here on our y-axis. We are limited in terms of our range, right? But this function does continue higher and higher in terms of range, right? It doesn't just end here. Now, looking at this function from the y-axis, if we're looking towards the left of it, I'm talking about the negative x region. If we say negative 1 times negative 1, it's going to give us a positive number. That would be a positive 1. Right. Negative 2 times negative 2, negative and negative, positive. Positive 4. Right. Negative 3 times negative 3, it will result in a positive answer as well, and that will give us an answer of positive 9. Right. Okay. So now I have obtained all the points that I can physically obtain for this function for the Cartesian plane that I have. And now we're going to go ahead and join them up and look at the shape of this function. Okay, so now that this function has been plotted for us and we can see the shape of it clearly on our Cartesian plane, I want you guys to take note of a few points, right? And these points will essentially tell you the properties of this function. The first thing I want you guys to take note of is the fact that this function has a turning point. That means that if I'm looking at this function from left to right, from the left for the first half of this function would be decreasing in y values until it reaches our turning point. If I continue towards the right for the second half of this function, it will now have an increase in gradient, an increase in y values as it progresses from left to right. Okay, that means we have two different types of gradients in this single function. We have a positive gradient and we have a negative gradient. Now, the turning point is also significantly important as it also gives us the axis of symmetry for this function. We can see that this function is symmetric about the y-axis. And this function over here, it cuts the y-axis at y is equal to 0, right? So that means that this function is symmetric about the line x is equal to 0. Another important point that I want you guys to take note of is the fact that this function cuts both the x and y axis at the origin, which means its x and y intercept is at a value of x is equal to 0 and y is equal to 0, right? Now, here's the tricky bit. When it comes to this function, just like the linear function that we did, as long as we have 2 points, we would be able to plot the linear function, correct? Now in this case, we need 3 types of data in order to plot this function. We are going to need the x and the y intercepts, as well as the turning point of this function. And if we have those 3 points, we would be able to plot this function without any problems, right? Now, when it comes to the properties of this function, I want you guys to take note of the domain and the range, okay? From the previous function that we learned, domain is all the x values for which this function exists, correct? And we know that this function will exist from a range of negative infinity to positive infinity. It will exist for the entire range of my x-axis. So the way that I'm going to denote that, the way that I'm going to write that down for the examiner would be x is greater than negative infinity, but x is less than positive infinity. Right. Another way for me to denote this would be x is an element of real numbers, because it is for all the numbers that are on the x-axis. And the final way for me to denote this would be x is an element of negative infinity to positive infinity. Right? Those are 3 very separate ways in which I can denote domain. You only need to denote it in one of these ways, right? Now, when it comes to the range of this function, here is where it gets a bit interesting. Notice that for this function in particular, the function does not have any y values that are in the negative y region, correct? So this function only exists for values of positive y. Now the way that I'm going to denote this would be in one of 2 ways. That would be y is an element of 0 to positive infinity, because this function only exists from a y value of 0 going towards positive infinity, as well as y is greater than 0, but it is less than infinity. Right, and there you have it, guys. Those are all the properties that you need to know for the natural parabolic function. That's it from me. All the best, and I will see you in the next one.